All right, here we go. Back for part two. This one, H, sum and difference rules. It says plus combos. Now, what's the sum and difference rule? Sum and difference means, well, if you've got two little functions added or subtracted together, you can take the derivative of them separately. So the derivative of a sum is the sum of the derivatives. That sounds familiar. It sounds like the limit rules. So just like in limits, if you wanted to split it up into its pieces, yeah, we can think of that as three different derivatives. And so here, if I wanted to take the derivative, it's just the derivative of this piece. Maybe I'll use it just, and by the way, you're not, you would never actually write this step in. I'm going to call this df by dx like this. And then it's the derivative of this piece. You would never, ever, ever write this step in, but I want to show you what I mean here, that I can split it up into the pieces, okay? The derivative of 82 with respect to x. And then, of course, this step you just do in your head and you go straight to the derivative, df by dx, and I do the derivative of this piece. The 3 comes down and subtract from the exponent. Here, if I wanted to think of the 5 out front, I could have the 5 out front, and then the 2 comes down, and I subtract off the 2, and then the derivative of a constant is just 0, and then there's my derivative of f with respect to x is 3x squared plus 10x, and then 0. We don't write it. Can you skip this step? Can you go straight from here to here? Absolutely, absolutely. Can I slide that? Yeah, I'm gonna cheat and slide that over so I have some room. Got two brackets multiplied, and notice there was no rule about the product of two functions, right? There was no rule back here about product rule. That's common, but there's no product rule. So how are we going to handle this one? Well, this is just two brackets. Any grade 10 kid would tell you that that's just screaming to be multiplied out, right? So again, we want to rewrite this in a convenient form. And by the way, this first step is something that you need to keep in mind this whole course, for sure, in this chapter, because the idea, if you change things a little bit, it makes your life so much easier. So here, I'm going to multiply this out. I get 2x squared minus 2 and positive 5. Minus 2 and positive 5 is positive 3x minus 5. And then I can take the derivative of this real easy. The derivative of this with respect to x, 2 times 2 is 4x to the exponent 1. I could leave that off if I want to. This 1 gets multiplied by the 3, and then the 1 goes down to 0. And so I'll talk about how to deal with that. And then the derivative of the constant is 0. And I'm going to tidy that up. X to the exponent 0, remember, is just 1. And so this is actually just 4x plus 3. The derivative of a parabola is a straight line. Wow. Okay, dandy. Let's keep going. Again, I don't have any, there's no quotient rule, right? I don't know how to take the derivative of a quotient. So what I'm going to do is I'm actually going to do this division. I'm going to divide the x into each of these parts. I'm going to rewrite this as q squared over x. And yes, you could do this in your head. You don't have to write the step out. But what would this look like? Plus 5 minus, I'm going to write it like that instead of like this, because then I can think of the exponent coming down and then subtracting 1 off of there and so on. So I'm going to go dq dx. I could go q prime, it doesn't matter. And then remember the exponent here is 1. So this is 1 times x to the exponent 0. This is the derivative of a constant is just 0. The negative 1 multiplied by this negative 1 is positive 1, x to the minus 2. Tidy this up a bit. And that's just 1 plus 1 over x squared. Remember, negative exponent means it goes into the bottom, and there's your derivative. Dandy. Now, what am I going to do with this? This kind of looks like something to the exponent 3. But we don't know how to take the derivative of what is actually a compound function, right? If this is a function in here, we don't know how to take the derivative of the function of a function, right? We can't do that yet. So how are we going to handle this? Much in the same way we handled that one up there, we're going to multiply everything out. And so I'm going to multiply everything out, right? Multiply everything by everything, blah, 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 multiply, 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 dot, dot, dot. That'll take you a step or two. And then you should end up with something that looks like, yeah, I got it right here, 8x cubed plus 12x squared plus 6x plus 1. And then if I take the derivative, all right, the 3 times the 8, you're getting faster at these, aren't you? You didn't have to actually write this term as that, did you? Because you just did that in one step. Well, I guess I did, but you're following along, aren't you? And then I know when the x to the exponent 1, that's going to go down to 0, so I don't have to write the x as 0 in there. I can actually do that. Derivative of 1 is 0, and there's the final derivative, all in one step. Lovely. This one looks nasty. This one looks nasty. But again, do a little work, rewrite it. The 4 acts on everything inside the bracket, so this is x to the exponent 4, 2 to the exponent 4 there, and I'm going to have to do something that's kind of a mess. I'm going to clean that up a bit. There, like that. 4 applies to both things in the bracket. How am I going to deal with this? I'm going to deal with it in the same way that I dealt with this. I'm going to divide each of these terms by x to the exponent. Well, what's the square root of x cubed is x to the exponent. 3 is the exponent. 2 is the root. So this is x to the exponent 3 halves. So I could write it like this. I'm going to clean this up still too, because I like having the variable on ground floor so I can take the derivative. But what am I going to do here? This divided by this is x to the exponent half, x to the exponent 3 halves. I'm still simplifying. I haven't taken the derivative yet. I'm going to write all the number parts out front, like write the k value out front, negative 3 over 2 to the exponent 4 is 16, x to the exponent 4. Then I'm going to write this as 4 x to the exponent negative 3 halves, right? Because it's positive on the bottom, it's negative on the top. Here, 2 exponents with the same base as x, and I've got to subtract the exponents, right? X to the exponent a half subtract 3 halves is x to the exponent negative 2 over 2, x to the exponent minus 1. And then now, each of these terms have the differentiable, the nice form. They're in nice form now. I can take the derivative. 4 comes down. If you're scared of the fractions in one step, then it's okay to write that extra step. Plus, yeah, okay, I'm scared of the fractions too. The negative 3 halves comes down. Then I got to subtract 1 from that if I need to do that in the margin. Well, that's 2 over 2, negative 5 halves. And then the negative 1 comes down. That becomes a minus 1, x to the exponent minus 2. And we're starting to get to the hang of this derivative thing, aren't we? Tidy this up. Negative 12, or I could cancel the 4 here. Negative 3/4, x to the exponent 3. Cancel the 2, negative 6. Oh, negative 6 over 1, isn't it? X to the negative 5 halves. And I could put that in the denominator if I wanted to. And over here, I suppose I could put this in the denominator, maybe tidy up one more step here. Minus 6 over the square root of x to the 5th minus 1 over x squared. All positive exponents. Okay, dandy. Still got a couple of examples up? Indeed we do. Let's keep going. The graph of that is given. Determine the equation of the tangent at x equals minus 1. So equation of the tangent, well, we need the slope of the tangent first, right? Slope of the tangent is given by the derivative. So let's take the derivative. the derivative of this one is easy peasy, right? 3 times 4, 12x squared. 2 gets multiplied by the 3, 6x, and that disappears. So if I wanted to find the slope at that, then the slope is f prime at minus 1. I substitute in minus 1 there, and I get 12 minus 6 is 6. Make sure I've done the arithmetic right. So the slope of the tangent, therefore the slope of the tangent is 6. And if I want to write y equals mx plus b, notice when x is minus 1, I guess I have to figure out what f at minus 1 is. Put in minus 1 in here, and I get, what do I get? I get minus 6. Minus 6, 4, that's negative 4, plus 3, minus 5 is minus 6. And so then I can fill in my equation. I got m is, my slope is 6, my y value is negative 6, my x value is minus 1, and then I can fill this in. If you're using the slope point form, yeah, that's fine. You can do that too. So what do I got? I got negative 6 equals negative 6 plus b. B equals 0. Is that right? B equals 0? Wow. So that means y equals 6x is the required equation. Dandy. Determine other points. So hang on. Does this make sense? At negative 1, yeah, negative 1, negative 6, there's that point that we said. Could I convince you that that would go through this point? Have a y-intercept of 0? Yeah, I think I could convince you of that. Absolutely. Then what does it say? Determine other points in the graph with tangents parallel to this graph. So, okay. Well, should be over here somewhere, right? Maybe another one? I don't know. Don't know. But here somewhere. It looks like maybe at positive 1. But how are we going to do that? Well, we know that the derivative, right? The derivative has to be the same value. And this is a lot easier with when I don't have to go from first principles. We know that f prime at x equals 6. So therefore, 12x squared plus 6x has to equal 6, and I can solve that. How do I solve that? It's a quadratic equation. All right, I'm going to divide everything by 6 to simplify this. And then good old factor formula, the two F words. Factor formula, I got 2x minus 1. And x plus 1 is how that factors. There's the one that I knew before. This is x equals minus 1. Here's x equals a half. So there's also at a half. Could I convince you at a half? Oh yeah, right there. There's where I said the line is parallel. Absolutely. Determine other points in the graph with tangents parallel. So then, therefore, another tangent with slope equals 6 occurs at a half, and then whatever that y value is. I don't really care. F at a half. Doesn't matter. Find the points on f at x that have horizontal tangents. There's going to be 2, right? Horizontal tangents would be, let's see, right there and right there. But I should get 2, right? There's a maximum there and a minimum there. And by the way, remember when in functions when we said we're going to learn this in calculus? Well, this is what we're learning. We're learning this in calculus. Find the point on f at x that have a horizontal tangent. So we know we want f prime at x, which is equal to 12x squared plus 6x. That's got to be equal to 0. So now I'm going to solve this. Well, how do I solve that? Factor away. So I have x equals 0, x equals negative a half, and then, therefore, there are horizontal tangents at 0, f at 0. And again, you can calculate the y point. Did I actually calculate? No, I didn't even bother on my notes. You should, really. And there's the x value, there's the y value. Dandy. Do I got one more? How are we doing for time? Is this going to be a part 3? Yeah, 15 minutes. I'm going to go and do example 3 in part 3 of this video.